let me see how many topics we have left. Okay, 3 weeks. Okay, we just have, but so that means in a day we have a test. If you can hear me, your test can be next week or upper week. If not next week, it's going to be upper week. So please take notes. If your CA is going to come up, it's either next week. If not, upper week. Please take notes. So that day we have a test. That means we're going to have a class that day and also a test. I mean, a class then the test, so that we can now finish up. We can finish up what we have to finish up. All right. So magnetic fingerprint in rocks, the paleomagnetism and plate motion. So core concepts: the rock as a tape recorder, meaning that there's a way rock records information. There's a way rock it records Earth history. So this introduces the concept of paleomagnetism, which is essentially the study of Earth's magnetic history stored in rocks. That means if you have a rock, no matter the form, you can, through magnetization or paleomagnetism, as it were, you can have information about what has happened years, thousands of years before that time. So think of it as a geological version of flight data recorder. You know what flight recorder is in an aeroplane? It records everything that happens in that aeroplane as it flies from takeoff to landing. Everything, the phone, the messages, the announcements, the paths that is taking, turning left, turning right, descending, ascending, and all that. So now let's describe this tape recorder concept. The concept uses the analogy of a tape recorder because rocks don't just feel the magnetic field, that is Earth's magnetic field, but they freeze it. When you freeze something, you make it stationary. That is the recording that we're talking about. When certain rocks form, they capture the direction where north was. Meaning, of course, if you can identify your north, then you know where your south is, you know where your west is, where your east is. And the intensity of the Earth's magnetic field at that specific moment in time. So we have the direction and intensity of the Earth's magnetic field when that rock is formed. That means as the rock are formed, at least you have an idea of maybe, okay, year 2, as you go along probably, or maybe second semester, you see the courses that will explain how rock forms and all that. But I know you have a slight idea. So geologists call this a fossil compass because, fossils are ancient information, ancient plant and dead plant and animal that are buried like dinosaurs, So it is most of those people that actually exhumed, the archaeologists that exhumed dinosaurs, they did not live when they were not alive. They didn't see them when they didn't go to see dinosaurs alive. It is the fossils that are buried that they discovered that made them create what happened those in that era. So it's more like, a compass is direction. So a fossil compass it's something that will give you direction on what has happened. So that's what we call rocks. We call this paleomagnetic formation from rocks as fossil compass. Now, if the tectonic plate moves to a different part of the world, now what is a tectonic plate? I'm not sure if you've done plate tectonics, but it's a course because this new system, I don't know where it falls now, but let me just say, the Earth is like a biscuit now. Let me focus on a rectangular or square biscuit. If you break it apart, it falls apart. So if you break it into two, it separates. So those when it was what happened now? When it was a biscuit, it's one plate. It's a slice of biscuit, a rectangular or square biscuit, is a plate. But by the time it breaks into, it breaks up, it breaks into two parts. So you have two plates. That plate, in terms of the earth is just like one plate before, then it breaks away into different forms, different segments. So that is it. It's now parted ways to different segments. So that plate that is breaking is as a result of tectonic activities, meaning earth movement, the movement of the earth. So it's either it's break as a result of compression or extension. That is what you still learn. Wait, oh, this class, I explained this thing now. Come on. That is in seismic something. What is that? Seismic. What's that called, sir? Seismicity. Yes.
GPH 122, sir.
I not say anything about
Introduction to
seismicity.
seismicity.
Yes, sir.
Introduction to seismicity. I think this is the class now. Yeah. So okay, thank God. So that will give you better information as regards plate tectonics. Okay, good. So okay. So even if the tectonics plates moves to a different part of the world, millions of years later, the rock still points to where the magnetic pole was, even when it was born. When it was created, or when it splits, it gives us. So this is where it splits because of the information in the rock on the plates. So it's just as okay, if you break a biscuit into two now, by the time you look at the property of that biscuit, and at the point of breakage, at that edge, and the edge, that edge, you know that they are the same. People can know that they were families together, they were the same. So the necessary ingredients for us to have this formation is what we call the ferromagnetic material. For a rock to record this data, it must contain specific mineral that act like tiny magnets. Tiny magnets, they are what we call magnetic material. So the magnetite itself, this is the composition of this magnetic material, Fe2004. Magnetite. It's a mineral. It's a magnetic mineral. This is the most important mineral. Okay. This is the most important mineral. So it is highly sensitive to magnetic fields. An occurrence, while found in various rock types, it is most prominent in basalt and igneous rock. Basalt is an igneous rock, so you see it mainly in this kind of rock. As basalt lava cools, these mineral aligns themselves. So now it cools. That means it's from molten form to solid form. So the state is behavior of magnetic grains at that state. So I will just want to explain how it moves from liquid to solid. What we are interested is the behavior of these magnetic grains. What state is it? Now, at liquid state, grains are suspended and free to rotate. They naturally align themselves with Earth's magnetic north, just like the compass needle. As it cools below the Curie temperature, as it cools below a specific Curie temperature, the atoms within the mineral loses the energy to juggle or to jiggle around, move. So at the solid state, the grains are locked into place. This creates thermal remanent magnetism, TRM, a permanent record that lasts for billions of years unless the rock is reheated, because that will change the alignment. So this is This is how these magnetic magnetites are formed and are very important in paleomagnetism, which gives us information about the rocks, when they were formed and where they were formed. So in summary, the key idea is certain rocks can preserve a record of Earth's magnetic field at the time of their formation, which acts as a fossil, so fossil compass. Now, essential condition is that the presence of ferromagnetic minerals. These are the primary minerals, magnetites, because in this rock, there are ferromagnetic material, which is made up of magnetites. And the rock that will find this magnetite more is the basalt. So it's like if you have plate tectonics in two different locations. If you see basalt here, look at the arrangement of the the magnetites. In basalt in the left side, on the splitted half, and look at another rock called basalt on the right hand, and look at it again. Do you have the same arrangement? Do you have the same alignment? That will give you, oh, these plates were together, but before together. Now they are because of tectonic activity, they are now split. Also found in some sedimentary rocks, so you can see some magnetic material in there. That's what we call detrital magnetites. They are just very few. And metamorphic rock as well. So it means that you can still have some of this, just few, but mainly it's in igneous rock, the basalt igneous rock. So this means that an analogy, imagine tiny bar magnets suspended in liquid rock. When they solidify, they lock into places. That's just the summary of what I explained. So thermoremanent magnetization acquisition. I see this. Look at this is when it was formed, but after it has cooled, you can see the ferromagnetic materials. You can see all the way they are scattered. It is now solidified. It is a molten form. It is now solidified. So I think this is just what is now way below the Curie temperature. All right. Okay. All right. So the recording mechanism, the thermoremanent magnetization itself that I mentioned earlier. That means talking more about this. Igneous rocks, which is basalt, forms at high temperature, just like that figure show, which is at temperature greater than Curie temperature. You can see that's more than 580 degrees Celsius. That's when they are formed. Above this temperature, atomic magnets are disordered. No net magnetization. That's why you can see it's just everywhere. Now, as the rock cools through the Curie temperature, the magnetic minerals align with the ambient Earth magnetic field. Okay, maybe. Okay, so there's now an alignment. Just hold on. Let me just check something if I can have another. Just a moment. Let me check if I can have a figure. Let me see if I have a figure that will show the alignment. But if I can't get now, probably before I send, if I still have it before I send the document to you, I might just add it to the document I will send later. Okay. I don't think I found it now. So let's just okay. Let's just continue. All right. So the magnetic mineral align with the ambient magnetic Earth's magnetic field. Now, upon full cooling, this alignment is locked in permanent in is locked in permanently. It's locked in permanently. I think that I explained earlier anyway. Why is this powerful? Thermoremanent is an extremely stable and strong magnetization resistance to later field changes. Example is compared to setting a password in hot wax. It's a fluid until it cools, then the expression is fixed. That's just an explanation, just an analogy to explain that. When it's liquid, it can be twisted and turned. That is why when it cools, it becomes permanent. The only time it can be changed is when it's been reheated. I mentioned that earlier. So let's see what how this discovery further explains the plates and paleomagnetization. Now, it was observed in 1950s. That's something years ago now. Scientists measured the paleomagnetic direction in rocks of a different age from the same continent. Paleomagnetic direction in rocks of different ages from the same continent, for instance, Europe. The calculated magnetic pole position moved dramatically over time. So meaning that as the ages changes, the magnetic pole position keep changing. The big question is, did the magnetic pole wander widely, or did the continent move? Now, the physical test is we plotting the apparent polar wander. This is APW parts from different continents. They showed different divergent paths. Now, this means that the poles have remained relatively near the geographic poles. That means the magnetic poles is very close to the geographic poles. The wander is apparent, caused by the relative movements of continents themselves. This was a key paleomagnetic proof of continent drift, meaning that it is not the pole that is shifting, but the continent that is drifting. I think I prepare something to better explain that concept. Now, this image, okay, I think it should be, okay, I didn't put the image. Let me see. Okay, I think the images are later found below. Let's hold down. Okay. Since the image are not immediate, don't let me put it here. This explains, okay. This explains apparent polar wander, APW, which is a major breakthrough in the 1950s that provides the scientific smoking gun for continental drift. Smoking gun in the sense that you know that it's just a phrase that's used to explain something that is correct, that you cannot lie. It's not a guesswork, it's original. Because when you see somebody holding a smoking gun, you know that the person has just fired the shot. So there's no evidence, there's nothing to show otherwise. So now, so that means this experiment, as was obtained in 1950, is a major breakthrough that shows that there's a drift in continents and not at the poles. Now let's continue. Scientists found that as they measure the magnetic signature in rocks of different ages. You know, I said, okay, let me just continue because the last slide I explained that different rocks were, but different ages from the same continents, you know, they were analyzed. Okay, now, scientists found that as they measure the magnetic signature in rocks of different ages in a single continent, the position of the magnetic north pole seems to shift drastically over millions of years. This presented a paradox, which is either the Earth's magnetic pole was physically wandering all over the globe, or the continents themselves were moving while the pole stayed relatively fixed. So it could be either of the two. I think the last class we spoke about that magnetic poles and knots and all that. Now, to solve this, researchers conducted a critical test by comparing the wandered parts of different continents, such as Europe and North America. They discovered that the paths were different and diverging. If the poles had been the only things moving, all continents would have been recorded at exact same paths, meaning the continent would not have moved. The conclusion was that the magnetic poles have always stayed near the geographic poles, making the wonder mere apparent. This divergence proved that the continents were drifting independently of one another, serving as foundational evidence of the theory of plate tectonics. So apparent polar wonder helps to prove the existence of plate tectonics. Meaning, you can see the world map. You can see somewhere here. This is what is it called? This is a continent of Africa. If you can fix these parts into these parts, so this has moved. So the North Pole remains the same, but the continent is drifting. So you can see this is called Pangeo. When you do the geology, I think there's somewhere you'll be taught how this Laurasia and Gondwana. So from Panji to Gondwana and Laurasia, the modern world, you can see how they were drifting, how they were shifting from one to now have this. So meaning that there's still small shift, small shift. So maybe in the next 1 million years, this will have broken again, or this will have merged with this, or this would have moved. The distance between this would have increased, or this would have moved closer to. You can see the things will have changed. So that is that. The smoking gun, the magnetic anomaly. This is just the proof that there exists a magnetic evidence that supports. There exists a magnetic evidence that supports that plates actually moved. Continental plates actually moved. Now the context is here is the sea floor spreading hypothesis by these authors in early 60s. That is like 10 years after that first one. And the fact is, Earth's magnetic field reverses polarity irregularly, normal and reversed epochs. This is a time in history. This is a time in history. Now, as new ocean crust forms, you know, we have the continental crust, we have the ocean crust. I believe you know the difference. So, but within the ocean crust now, when there's new ocean crust as it has formed at mid-ocean ridge, MOR, it cools and records the prevailing magnetic field, which is at times it will be normal, it will be reversed. Now, the ocean floor becomes a series of magnetic stripes, symmetrical bands of stronger normal and weaker reverse magnetic signal parallel to the ridge. So, Van Matthew Molly hypothesis 3 years later linked these stripes directly to the seafloor spreading plus field reversals. This provided the quantitative mechanics evidence that transformed plate tectonics into a stable theory. Now, what does that mean in full? Last slide, that last slide is what I've explained in details with this slide. I'll copy. Don't go to, don't read before I make. So I believe you have read through. I want to just go through it before I make my own explanation. In fact, it is just what it is just like explaining the last slide, better understanding. Now, the definitive smoking gun for this theory came in the 1960s with the study of marine magnetic anomaly in the ocean floor or on the ocean floor. Scientists realized that as the new ocean crust forms at mid-ocean ridge, it cools and records the Earth's magnetic field, which irregularly flips between normal and reversed polarity. So this is the cooling. It cools and records the Earth's magnetic field. Now that record now shows that it has irregularly flips of normal reverse polarity. This process creates a symmetrical pattern of magnetic stripes on either side of the ridge, meaning that, okay, let's just continue. So the Matthew Molly hypothesis successfully linked these stripes 3 years later to seafloor spreading, providing the hard quantitative evidence needed to transform the idea of moving continents into the robust, testable theory of plate tectonics we use today. Now, what does that mean in essence? Look at this. This is the ocean floor, the continent crust, not continent, ocean crust. So it splits, it breaks into parts. So now the magnetic reading shows that if normal magnetic polarity at a point, this is around the ridge itself, it has normal magnetic polarity. After a point, it's reversed. After normal magnetic, reversed like that. As it moves, as it moves. So meaning that it starts from A. So here at A, we have the magnetic polarity, which is normal. As this moves up, then we have the reversed occurring. Then this moves again, another one comes. Now, if that is measured, let me, okay, use this. You can see if that is measured and quantified or calculated, you can see the stripes. These are the stripes. And what you can notice that the wider the stripes, the higher the magnetic field being recorded. You can see this one too. At this time, at zero, at the beginning, C-floor spreading begins. You see, after a time, after the Earth's magnetic field flips and C-floor polarity reverses, then this will move again. The another one, it flips again. That magnetic flips again, forming a new stripes of normal. So reverse normal as it moves, showing that movement of continents, showing that there's a motion that looks as if it's sinusoidal, up and down, up and down, up and down. So when the sun up is peak, down is trough, up is peak. So that is also what formed that zigzag on and off positive normal, I'm sorry, normal reverse kind of polarity. Now let's do some small calculation. This is how we turn magnetic pattern into quantitative plate velocity. Now the formula is spreading rate equals to distance over time, just like velocity now. Half spread rate, speed of one plate moving away from the ridge. The full spreading rate is speed of separation of the two. That means you multiply by 2, the half. This half you have here multiplied by 2, so we have for the two sides. Now, a magnetic anomaly profile across the the mid-Atlantic ridge shows a prominent anomaly 50 kilometers from the ridge axis. This anomaly is identified as the Jaramillo whatever of that normal subchrone, which has an age of 1.0 million years. Calculate the half spread rate. So that just means the distance is 50 kilometers. So to centimeter is this, 5 million. The time, the anomaly is identified, which has an average of 1 million years, 1 million. The half of that is this multiplied by this. That is, this distance is divided by this. Half spreading rate. We have this, so we have that. This means that the North American plate is moving away from the ridge at approximately 5 centimeters per year. About the speed of your fingernails growth. So if you want to calculate the full, just multiply this by 2. That is 10 cm per year. Now, putting everything together now, from rock to revolution, magnetism bridges mineral scale physics and global scale tectonics. Mineral scale physics, meaning that you just pick a rock and gives us a global information about tectonic or plate tectonics. Thermoremanent in basalt, that is magnetism in basalt, explains how we got the magnetic stripes. The seafloor supports this spreading rate. Eventually, we were able to see that quantitatively, there's what we call plate tectonics. The integrated geology history, apparent pole wonder parts allow us to reconstruct ancient continent latitudes and orientations. That is paleogeography. Evidence for internal forces. The symmetry anomaly pattern is a direct manifestation of the mantle convection and the generation of new lithosphere at ridge. So final thought, paleomagnetism provided the irrefutable quantitative proof that turns the controversial ideal of continental drift into the robust unifying theory of plate tectonics. So meaning that the drifting was a contentious issue at that time. But after the 1960s, that was put to rest. So advanced discussion, critical thinking, what might happen to the magnetic anomaly pattern if the rate of seed floor spreading changes over time? Answer, the stripes will be wider or narrower, providing an history of the rate of change. So that's why I said the narrow, when it is narrow, you can see the magnetic field anomaly very small. When it's wide, it's very big. So there's information here. That's why I decided to put this for you. The mention, not all rocks are ideal recorders. Like I said, what are the major recorders? The basalt rocks. What geological process might alter or erase this primary TRM, e.g., severe metabolism, lightning strikes, chemical alteration, heat. Now, modern application, how is this knowledge used beyond reconstructing the past, e.g., in exploration geophysics to understand crustal structure in calibrating the geological time scale? So, I've given hints to all of this advanced discussion, where to think and all that. So, like I do, you have question, and as well, which helps you in understanding the thermoremanent magnetization. And I also have included the solution. I also have information regarding apparent polar wonder APW, which shows that what is moving is actually the plates and not the magnetic knots or the poles. This is the question, this is the answer, this is the question, and here is the answer as well. So any question? Any question?
So are you going to get this slide?
You said?
Are you going to
Somebody
get
asked
this
the
slide,
question.
sir? Yes,
David,
sir.
go ahead.
So I was asking if you're going to get this slides.
That's supposed to be a question. Does that mean you don't get the slides before? All the work I've been sending, you don't get it. David, is it that you don't get all the 3 or 4 classes we've done before? You don't have the slides. Is that it?
Sir, I have it, sir. We have it, sir.
So why is that supposed to be a question? All
We
right.
don't have this slide for the last class we had.
You don't have the slides.
Yeah, the last one.
Class rep. Is class rep
Sir.
here?
Yes, sir.
I did not send the last slide, the last material.
No, sir. No, sir.
I
It was
did not
only
send
the one
it.
for geomathematics. It was only the one for geomathematics you sent.
Wait, let me check. The last topic was Earth's magnetic personality or something like that. The mathematics is on Friday now. I had that on Friday. So then you don't need it now. If you need it, you have asked me. If I keep sending all the courses, all the slides, and somehow I didn't send a particular one, I hope I did not send it to the wrong person. And nobody asked me. Then you don't need it. Probably you need this one. That's why I asked. So I'll send this one to you. I send my and this thing you do it's not online. You can't get it anywhere. What this material I'm sending to you because I created them. So if you need it, you ask me that, oh, the material from the last class. But for now, I don't think you need it. So it's okay. So any question? I want to believe there's no question now. So
Stop please.
I will.
Sorry, sir. Sir,
No, it's not a matter of apology. I'm just saying, if you need it, you will ask. You have not asked. You only asked for this one. But I thought anytime I
no,
finish,
sir.
maybe because I was working
We
on,
are
maybe
waiting, sir.
just like what I
We are
said I
waiting,
would
sir.
do. I said I would check one or two things here. If I can see more diagram to better explain certain things, I will send it. I will add to it before I send it. So I guess maybe that was what I was doing, or I had to do before sending it. Because I don't hold it at all. I send it immediately. I create it.
Oh, we are expecting,
I have
sir.
created the material already. So why would I send it? Why would I send
Yes,
it?
sir. Sir, please send it, sir.
Okay, so no problem. So next week, if you don't have the CA, I'm repeating, next week, so just start preparing for your CA. I don't want to hear story, but we'll definitely have it on the next week. I mean, Wednesday should be on the 11th, which I'm not sure we're going to have it, but if you don't have it, be sure rest assured on the 18th. Okay.